Let's beginning with chapter 11. We're going to be talking about kinematics of particles. Um, in this chapter, we're going to learn about how to decipher, how to capture, how to calculate instantaneous velocities, and how to compute average velocities. Also, we're going to understand and compute velocities from position and accelerations. So when they give us a position, in this chapter is going to be a function of time. Okay, there only is going to be just a single function of time. It's not going to have x, y, and z. It's going to only have a variable time. And when we derive that function with respect to time, we're going to get velocity. So position, velocity. When we derive again, we're going to get acceleration. Okay, so let's see how that looks. First of all, the objectives are to describe the basic kinematic relations between position, velocity, and acceleration. So we're gonna understand how to compute those and how to create relationships between them. So the basic relationship is a derivation and an integration between them. We're gonna be solving problems using these relationships, and we're gonna be able to define velocity, acceleration, and position in Cartesian coordinates. Later in other chapters, we're going to use polar coordinates and spherical coordinates depending on the problem. We also want to define the tangential and normal, as well as the radial and transverse coordinates. Okay, we're going to analyze the relative motion of multiple particles. So this is where things start to get interesting, because we can create a system of particles and see how one moves with respect to the other one, and that is very interesting because, again, take planet Earth and take a satellite and take another satellite. We have to understand how one particle moves with respect to the other one so that they don't collide. There's not a collision between them. Okay, we gotta determine which coordinate system is the most appropriate for solving the problems. So again, we can have x, y. If it is x, y, and t, most likely it's going to be just t and x to start with. But also there are other coordinate systems. As you know, we have spherical and polar, etc. So this is polar, where we have a radius at the angle. Also, we're going to be calculating the position, velocity, and acceleration of particles in rectilinear and curvilinear motion. So let's take this quick introduction to mention that kinematics is, or the kinematic relationships are used to help us determine the trajectory and accelerations of a system or a body for a given path. So the path is the function itself. So the function will tell us the path that it follows. The velocity is derived from the position, and the acceleration is derived from the acceleration. So kinematics is used to determine the trajectory and acceleration of a system. So obviously this system has a constant mass. Okay, so forces can change and accelerations can change, but mass is the same. So the satellite is going to have constant mass, this system will have constant mass, this space station and this airplane will have constant mass. Alright, so the correct definition is that kinematics is the study of geometry of motion. Okay, so how is the motion of a body exactly? How is that motion? And as we said, it relates displacement or position, the change in position, the velocity, acceleration, and time without reference to the cause of motion. Okay, so it relates the displacement. The displacement is the change in position from here to here. There's a distance x. That is the displacement. The velocity, which is the derivative of x, the acceleration, which is the derivative of velocity, and time without reference to the cause of the motion. So in this car, there's a force given by the engine. Actually, they're forgetting the force of friction here, which is about 60% the force of the of yeah of the force going to the right hand side. I'm not gonna say the force of the engine because the the force that is making the car go to that is making the car move. There's a force of friction to the left, which is about 60% of the force that makes the car move. For a dry surface, it's only like 10 or 15%, maybe 20% when it's wet. Um, and the design of tires actually come into create more friction between the wet road and the tire. But anyway, we have the force that makes the car move, we have the force of friction, then we have the drag force, which is the force that is preventing the car from going faster, and then we have a force of gravity, the mass of the car times the acceleration. Um, and then of course we have a normal force here at the bottom. So this system is just wanting to introduce some new concepts, which is the drag force and the drive force. But we knew some of them already from statics. Okay, so this is called the free body diagram. And the complete system of forces is there's a force making it move. There's a force opposite to this force, which is the friction force. They call it this force drive. There's also a drag force, F drag, and then there's this force to keep the car down, the weight, and there's a normal force keeping the car from going um, from lifting, or from there's a normal force keeping the car from going into the ground. Okay, now there's a different concept, which is kinetics. And kinetics is the study of the relationships existing between the forces and the body. So in short, kinematics is the geometry of motion, all right, relates displacement, velocity, and acceleration without the cause of motion, versus kinetics studies the relationship between the forces, which is what makes making the system move, acting on a body, the mass, and the motion of the body. Kinetics is used to predict the motion caused by given forces. So kinetics is what you're going to be studying in mechanical engineering, aeronautic, and physics to predict where the system will be in 1 second, where the system will be in 3 days. Kinetics is what the um, the studies or the simulations made to analyze the weather. The weather is a kinetic simulation because they're trying to predict what's going to happen tonight. All right, so that's the difference between kinematics and kinetics. Kinetics definitely focuses on the relationship between the forces and the mass and tries to predict the path, versus kinematics is simply the study of how of the movement itself. All right, so in rectilinear motion, we're gonna have position, velocity, and acceleration of particle that moves along a straight line. So this part is very confusing for some students. So say a race, this is a straight line, okay, the x direction, but in that straight line you can have different accelerations and different velocities. So you can have a very fast pace up to here and then stop come to a stop here. So the motion is straight, but the velocities and accelerations are not. So don't confuse the path with the relationship between the displacement and the position and the acceleration. All right, because the relationship is not linear. It doesn't have to be linear. It could be that they give you a relationship with the velocity, with the position, is saying that something like that, meaning that at 1 second it moved 1 meter, but then in 2 seconds moved displaced 3 meters. So the path is linear, is at a straight line, but the way how that happens doesn't have to be a straight line. Okay, and that's the function itself. Versus curvilinear motion is motion where position, velocity, and acceleration of the particle is moving along a curved line. Okay, so rectilinear versus curvilinear. It's pretty straightforward. All right, so the basic concept about a rectilinear particle moving along a straight line is that you always have the origin and the movement has a direction. So if you move to the right, you move with a positive direction. If you move to the left, you move with a negative direction. So if the center is downtown and you go, say, north, you're moving with positive coordinates. If you move south, you're moving with negative coordinates. Or you could have said that is north is, you could have said that north is negative coordinates and south is positive coordinates. That depends on your coordinate system. All right, here they're saying it's positive to the right and positive to the right. So anything that goes to the right is positive and anything that goes to the left is negative. Same with velocity. The velocity that's moving to the right hand side of this system will be positive velocity. And a velocity that is moving to the left hand side is negative velocities. Okay. Accelerations is the same way, except for acceleration is a force. So if you're having a negative acceleration, you're losing speed, or that you have to know the point before. That's why it's going to be a function. You're going to have to know what's going on before. It could be that you're going to the right hand side with losing acceleration, or you're gaining acceleration on the left hand side. So this acceleration part is very important to know the point before. So the position, as we know, is going to be defined by x and is defined by negative or positive distances. The motion of the particle is the position along the time. Okay, so we're going to look at this example in detail. And we're going to look at that example in detail, but first let's go over some other concepts, which is the average velocity. We're going to talk about that in detail too, but it's just basically the amount of distance in the amount of time. And the instantaneous velocity is the exact moment in time where that change in distance and the change in time occurred. All right, so we're gonna take a whole we're gonna take our time going over this example. Let's go over another example here. All right, let's go over this example because we're gonna have that whole example to explain how to do homework. So so in case I didn't make myself clear, this example right here, I'm gonna save this for next lecture, and I'm gonna show what tools to use so that we can do our homework with it. Okay, for now I'm just gonna do this example right here. So the position of a particle moving along a straight line is defined by the relation. Okay, so they're giving us the function. So the function with independent variable of time is equal to time cubic minus 6t squared minus 15t plus 40. All right, so if you derive this, it's going to be 3t squared, right, minus 12t minus 15. So this is the velocity, and this is the acceleration. Okay, so the plot for this is, which by the way, if you have a graphics calculator, this will be the time to use it. If not, next example, I'm going to tell you how to use Wolfram Alpha so that you can use that for your homework and your exams. But for now, let's just focus on what it means. To just compare functions for space or displacement, velocity, and acceleration. So the plot for this graph, or for this problem is a cubic curve, okay? And they're basically saying that it starts at 40, it goes up to negative 60, where it changes direction and goes almost back to 0. All right. And one of the questions is A, time at which the velocity is 0. Okay, so that's pretty simple. This is the position. We have to find the velocity. So the velocity is the derivative, and we just derived that. So plot this, and again, if you have a graphics calculator, use it. If not, I'll show you next example how to plot it with Wolfram Alpha. But this function, if you plot it, will give you something like this. And right now, the velocity, which is right here, is 0 at 5 seconds. So you see how this graphic method is very useful, because we already solved the first problem. At what time is the velocity 0? Okay. You could actually have known from this, because there's a minimum. So remember, when you derive a function, this point right here, this tangent minimum point right here, tells you that it's going to be 0. In other words, if you review your calculus book, you'll see that when you have a local minimum or a local maximum, this change in curvature will give you, when you derive it, that means that this is a 0 crossing. But anyway, if just derive the equation and plot it, derive the expression, plot it, and you'll find the cross at 5 seconds. So the next question is the position and distance traveled by the particle at that time. Well, so that is also pretty simple, because they're asking you the position and distance. So for that, you're basically having to go back to your position function, and is at 5 seconds, you're at negative 60 feet from your origin. Okay, now the acceleration of the particle at that time, so you have to derive the velocity function one more time, and this derivative is 60 minus 12. Please go ahead and communicate with me if you're not familiar with derivatives. At this point, I'm assuming that you know how to do derivatives. Communicate with me via email if you have any issues with deriving functions. I'll also show you how to derive these with Wolfram Alpha to make your life simple, because right now I'm assuming that you already know this, but to save time, we're going to use a software to derive things. Anyway, so this function is 60 minus 12 is a linear function, so is a straight line that will help us solve some of the questions about the acceleration. So when velocity equals 0, you take the velocity function and plug, you just put 0 wherever you have a 0, wherever you have t, and then that will basically mean that you have your t equals to, let's see what the question was, time at which the velocity is equal to 0. Yeah, we have that already solved. The position and distance traveled by the particle at that time. Oh, okay. Position and distance of the particle traveled at that time is, you take time equal to 0 and place it in your function, which is this function, or you go to t equals 0 here and find it. So both ways will take you there. So if you place 5 here and use your calculator, or if you go to the graph, you'll be able to see that your position is negative 60 feet. Acceleration when velocity is equal to 0. Again, they're asking about acceleration, so go to your acceleration curve, and it is right here. If you're plotting it, you can see what that is. They didn't give us this number, so we're gonna have to just go ahead and check. Acceleration would be equals 0, so that is at t equals 5. So we go here and we're basically gonna replace 6 times 5 minus 12. This is equal to 6 times 5 is 30, minus 12 is 18 feet per second squared. Okay, and that's positive. Distance traveled from T4 to T6. All right, that's also very simple. So distance travel, so distance is here, velocity is here, acceleration is here. So notice that every time that they ask what is acceleration when velocity is 0, so velocity is 0 at 5 seconds. A lot of times you're gonna have to find what is the when is that happening. So we know it's 5 because it's crossing 0, or here this is equal to 0, and then solve for the roots. And this is going to give you two roots, but I can tell you that one of them is going to be negative and the other one is going to be positive. Well, the negative is not going to be true because it's not, you don't have negative time in these type of problems. You're not going back in time. So it's the positive root, or simply plot it and see that it's 5. So that's why we're doing at 5. We just plug 5 here, or 5 here. You plug it in, or just come here and then, oh, okay, that's 18. So that's simple. 5 and the position is negative 60. But the same thing. If they ask you when is the distance, when the distance is 0, so distance 0 is right here. Say this is 2, I don't know what this is. We should check with Wolfram alpha later. But say this is 2 point, I don't know, 2 seconds. Then at 2 seconds, what is the velocity? So you come and you check here, and actually, yeah, it's 2 seconds. Interesting. Okay. All right. So they, as the same way that the local minimum in this plot is the change of sign in velocity, the same way this local minimum of velocity is the change of direction, the change of sign in acceleration. All right, but to solve the question, the distance between 4 and 5 and 6. All right, so if you have your calculator, you just evaluate between here and 6 and check what distance is. So the distance would be that and this, but we don't know for sure unless we plot it. So what we can do is do this twice. Do x at 4 equals and x at 6 equals. Find those two values. And actually that's what they're doing here. So distance from 4 to 6. So x at 4 is 4 cubic minus 6 times 4 is negative 62 feet. Okay, so at 4 is negative 52. And then you do the same thing at 6. Oh, they have a typo because they meant from 5 to 6. Yeah, because they're doing x5 minus x4. If you see, they're doing x5 minus x4. We have find this, and this is the one that we already had. That's negative 60. All right, so it actually is pretty simple then, because this is the difference between here and here. But you can also do between any second. See, that's why it's instantaneous, because you just evaluate the function at any time. And you can have your distance. So in this case, the difference between x5 and x4 is negative 60 minus this one, minus 52. Okay, so negative 60 plus 52 is equal to 8 feet. Okay, but since it's negative 8 feet, that means that it's 8 feet in the negative direction. Okay, so this right here is 52, so the distance here is 8 feet. But since it's negative, means that from the origin, this is traveling in a straight line for 8 feet. The velocity of a particle is always positive. The velocity of a particle is always positive? No, because from the origin, you can have positive velocity or negative velocity. The velocity of a particle is equal to the slope of the position time graph. So actually, this is true if you understand that slope is the change of something. So like if you have a function and you consider that every point here the slope, because it's instantaneous. So between here, this is a concept from calculus, right? From here to here there's a slope, from here there's a slope. So in that case, yes, because the velocity of a particle is equal to the slope of the position time graph. And that's what we just did. We have x, we have x time, and that had some type of function. And then v time was based on the derivative, or basically the slope of this function, right? So this is true. If the position of a particle is 0, then the velocity must be 0. And it's not true, because remember that what we just had, they're saying that if the position is 0, the velocity must be 0. That is not true. It could be negative or positive velocity. Position being 0 just means that it's crossing the origin. You can be crossing the origin towards left or towards right, and the velocity just means what direction is your system going, at what speed and direction is that particle moving. So this is not true. If the velocity of a particle is 0, then the acceleration must be 0. It's the same case, not true, because we just had that example before, where look at this, let's see, was the velocity 0 here? No, we actually didn't have a case where the velocity is 0, but I mean, it's not starting from 0, okay? But look at this case right here. Our distance is 0 and our velocity is not 0. And at that point, the acceleration is 0, but it doesn't have to be 0. It's just depending on the function itself. So that is not always true. Therefore, that's not correct. So the answer is the velocity of a particle equal to the slope, or the derivative of the position time graph. Okay, now we're ready to move to the next concept. So determining the motion of a particle. Okay, so acceleration is given as a function of time. Acceleration can be also given a function of position, and acceleration is given as a function of velocity. Okay, so acceleration as a function of time is what you just did before. This is time, this is acceleration, and whatever plot you have here is your acceleration as a function of time. But you can also plot acceleration as a function of position. Okay, so is in that case will be a as a function of position, is changing with time. Or actually, no, that's not what that means. Sorry. x and acceleration. Yeah, so changing in position and acceleration. So whenever you have 2 meters, what is your acceleration? 1 meter per second squared. At 5 meters, what's your acceleration? And you also can have your acceleration as a function of velocity. So be careful with what they're giving you. So the question is, can you think of a physical example of when force is a function of position? Well, there are there are many examples. Remember, position is relevant to a coordinate system. So if you place your coordinate system on the center of the Earth, then studying the movement of the planets could be very useful when you do a system when you do acceleration as a function of position. Okay, so for relative motion, that would be pretty useful. Also, a simpler system is a spring. Okay, so and actually remember when during the introduction that we talked about springs. So in a spring, you have x, and let's say to change things around, we're gonna say that this is positive x, and this is that's positive x, and this is positive y. So actually this is y, not x anymore. Let's say this is y. All right, so the acceleration as a function of position is very useful because then you can know exactly where the spring goes when there's a force. Okay, so in that case, it's very useful, right? You can see how that you can exactly decipher, you can predict where the object will be in space as a function of the forces. Remember, summation of forces is equal to mass times acceleration. Now, when force is a function of velocity, we have something called drag. And this is something very useful for airplanes and for cars. Is the force, as we saw at the beginning, is the force that is preventing the car from moving forward. It's a type of friction, but not because of the road, it's just because of the air around it.